This is lecture 3 for chapter 5, calculus 3. It is on conservative vector fields. If you have a scalar function and you take its gradient, that means you apply the del operator to a scalar function, you get out a vector. It is the gradient of f. The partial of f with respect to x in the I direction, partial of f with respect to y in the j direction, partial of f with respect to z in the k direction. So let's just say I have some function, for example, sine x plus cosine y plus z squared, and I take its gradient. When I take its gradient, I get this vector function. I can call it f because it is a vector field. So using our notation for this chapter, capital F boldface means a vector function that is a vector field, and that's what I have. Once I've taken the gradient, I could call it the gradient field also. Now let's look at it in the other direction. Say you had a vector field, and that would be right here, which would be f. Whoops, I didn't pick up the pin to pick up f. Okay, say your vector field is the gradient of some scalar function f. So f is equal to the gradient of f. Then you could say that particular vector field is conservative. The scalar function is called the potential function of f. So this incomplete circle here was supposed to circle the word is. So what I did in the previous slide is show that you could consider the gradient of a vector to be a vector field. On the other hand, if you find some vector field and you can figure out that it is a gradient of a scalar, then it is said to be a conservative vector field, and that's what the topic of this lecture is. There are two very important fields that are conservative. One is a gravitational field and the other is the electric field. And they have potentials. The potentials, remember, are a scalar function. This scalar function gives a scalar value throughout the domain, well in this case throughout R3. The gravitational potential is what you call the potential function for the gravitational field. So here's the little f for the big F of the gravitational field. For the electric field, the potential is called voltage. Now here we're going to start getting to the test for whether a vector field is a conservative field. I mean, you might say, well, it's a scalar function of some potential, and you could go looking for your potential forever and maybe just not find it, so you wouldn't know. But there is a test on the vector field itself to say whether it's conservative or not. So we start to work up this test by noting that if, let's say f is conservative, that is, it's the gradient of some f, right? You can then equate the components. The I component of f had better be the first derivative, first partial of f with respect to x of the potential function. And now I'm going to try to change some colors here. So the j component of the vector field is the y derivative. And let's see here. There used to be easier ways to change colors. Okay, the p is associated with the z derivative. Okay, so you have this association right there, and now let's look ahead. This is what we got from the previous slide. M, which is the I component of the vector field, is equal to the x derivative of the potential. N is associated with the y, p is associated with the z. Okay, now let us take some more derivatives. Let's take the derivative of m with respect to y and take n with respect to x. Okay, what do we get if we take the partial of m with respect to y? We would get the mixed partial, the second derivative of f, and then it would be, let's write it here. So we would have m sub y would be f xy, n sub x would be f yx, and you can see where this is going from the previous lecture. If Clairaut's theorem applies, you can take these in any order. Okay, do the same thing here, n with respect to z, and then p with respect to x, n with respect to x, and p with respect to z. So you're going to end up with all these mixed partials. So equating the mixed partials for the potential function that basically are the same, you would have the partial of n with respect to y would equal, now I have to go to the pen here just a second. So let's look at it like this. Okay, we're assuming Clause's theorem holds, that is, there you have all partial derivatives, all derivatives of the function, of the potential function, are continuous. So m with respect to y would be f y x, which would be, whoa, what happened there? That should be fxy. Oh, I know, I already switched them, sorry. So m with respect to y would be fxy, and n with respect to x is fyx. So if you can take these in any order, that would mean that these two would be equal, hence the derivative of m with respect to y would equal the derivative of n with respect to x. Alright, I hope you followed that rather long and involved statement. Now, you can go down here and see that I'll put it in different colors. Well, maybe I will, maybe I won't. Okay, here we go. Okay, the partial of p with respect to x and m with respect to z gives you the component functions, the second derivative with respect to x and z. And if you can take them in any order again, then they're equal. Therefore, those two terms are equal. And now, looking one more down, p with respect to y would equal n with respect to z. In other words, at this point, if these relationships, these three relationships hold, this one, and this one, all three of these hold, then you know that the function f, the vector function f, is conservative, and that it is equal to the gradient of some scalar function. You don't care at this point what the scalar function is at all. All you want to know is if these components, these derivatives are equal, then you know it's conservative. Later on, if you want, then you can go look for this at the potential function. But this is the component test to tell you that the vector function you have is conservative. So here's just a statement of the component test for conservative vector fields. F is some vector, okay, with the usual components of. So F is some, whatever m is, in the I direction, in j direction, p in the k direction. So you have these three functions. You take their partial derivatives, and if py equals nz, and px equals mz, and my equals nx, if those three hold, then it is a conservative field. That's the component test. You don't have to look for the potential function. All you do is look at the function you have, the vector function that you're talking about. So here's an example. Let's say we have this vector function, e to the x cosine y in the I direction minus e to the x sine y in the j direction plus z in the k direction. We want to know, is it a conservative field? So we apply the component test. We have to take the derivative of p with respect to y and compare it to the derivative of n with respect to z. Well, here's p. Its derivative with respect to y is 0. The derivative of n with respect to z is 0. They're both equal. Okay, so this one's okay. Move over. Take the p with respect to x and compare it to m with respect to z. P with respect to z is 0. P with respect to x is 0. M with respect to z is 0. This one's okay. The third one. Take the derivative of this with respect to y and you get negative e to the x sine y. Take the derivative of n with respect to x and you get negative e to the x sine y. They are equal. Okay. All three of these, this component test, the three parts of it hold. Therefore, this vector function is a conservative vector field. Just for comparison, here's one that isn't. Here's a vector field, x, y in the I, x, y in the j, z, zx in the k. All right, the first part, p sub x is z and m sub z is 0, so this doesn't work. Okay, so right off the bat, the first one is no good, so this one didn't work, and right now you know it's not a conservative field because all three have to hold. But continuing, n with respect to x is y, m with respect to y is x. This doesn't hold either. And here's one, this holds, but that's not good enough because, well, actually there's two, but you could even just have one failure and the whole thing wouldn't hold. So this is not a conservative field. One of the reasons we like to find out if a function is conservative is because there are several important properties of conservative fields. One is the line integral of a conservative vector field is independent of path. By the fundamental theorem of calculus, if I'm taking the integral of this derivative, I get the function itself, which I can then evaluate at the endpoints. So a corollary here is, what if these endpoints are the same? Well, obviously conceiving this integral, it's the same, and this would be 0. Another property is that a conservative field is irrotational. Irrotational means that the curl of f is 0. Whoops. So curl of f would be 0, and the reason that holds is because f is the gradient of a function. So we're saying the curl of the gradient of f, and this is one of the del identities. It's identically 0, so the curl of f itself is 0, meaning that the conservative field is irrotational.